Yeah. So before we're gonna do learning, maybe I was gonna maybe there's no it's impossible to how to say. Maybe I'll do like completely elementary computation, which for the benefit of those who haven't done the homework. Namely, suppose M is the simplest possible algebraic variety of the whole, just C1, just a fine, just line. Right? So what is this thing chi of square root of its canonical bundle? What's that? So well, let's first do the chi of just functions of M. Well, it's an affine variety. It has only sections. So it's only H0, no hierarchy homology. So it's just a trace. So this is just as functions. So it's a polynomial in one variable, x coordinate here. And we'll compute the trace. So there's an element T in GL1 acting on here. When I compute the trace of this element T acting in the polynomials, what do you think it's going to be? So right, it's almost correct. It's 1 plus T inverse because it acts x is a coordinate plus this. So it is this 1 over 1 minus T inverse, right? And then the canonical bundle is, again, it's the dual of this. So the weight of the canonical bundle is, so canonical has weight of that is T inverse. So if we want the square root, there will be square root here. So this would be T minus square root divided by 1 minus T inverse. And so it is 1 over this little a hat function of T, where that a hat function I defined to be T square root minus T minus square root. And so now if we generalize this to, so we'll go over there. So if we generalize this M to be Cn, then of course if I take my matrix to be diagonal matrix in GLN, then by exact same thing, the trace of that element T acting in this Euler characteristic of square root of M would be now the product of 1 over a roof hat Ti. Right? So these are somehow nice smooth algebraic varieties. The moduli spaces at which we're going to look, they have not just deformation, they have abstractions. It is to say they're defined by like a vanishing of a section of a certain bundle, and that bundle is the abstraction bundle. And so there, you're not going to get only the denominator, also the numerator. The numerator comes from the abstraction. So these are, and so this is when we were summing. If you remember what the series was, and now we can go back. We can go back here. What was this? So we were summing in this baby example the moduli space M was the Hilbert scheme of points in C3. It was cut out inside. You look at any, so these are 3 commuting matrices with a cyclic vector. They were cut out in the set of all triples of matrices with commuting with the cyclic vector by some equations. So when you do this, so this was denoted F. F was just triples of commuting matrices. No, sorry, triples of matrices, no commutation relation, and the cyclic vector, that was F. The tangent space to that at a given thing, it's easy to compute because it's just 3 matrices. So if you have a vector space, if you know the character of the vector space, you know the character of, at a fixed ideal, the torus character of that vector, of that quotient of the whole ring by the ideal is just the somehow generating function of the cubes in this partition. So that's the character of your vector space. Now if you want to compute the character of endomorphisms, these matrices, it's just that character times its conjugate. So that's easy to compute. And you put all these things in denominator. and then since it's the bundle of which, so this is a critical point of some function, that is to say it's cut out by a section of the cotangent bundle by the differential of that function. And the weights of the cotangent bundle come at the opposite of the weights of the tangent bundle, except the function itself had a certain weight, namely the determinant. So these are the weights. So these are the weights you put in the numerator. And so you sum the series up. And turns out, so in this particular instance, and we'll see it generally, so then the answer would be that this is some representation of this, some virtual representation of GL3 in this case. And in fact, we'll see this representation is symmetric algebra of some other representation. In other words, its character is obtained from some other character by via this transformation. And as we discussed, this transformation just amounts to like taking the logarithm of a series like this. And so what is this representation? This representation, I claim, is something that looks in denominator, it has as if we're on C5. And in numerator, it has something. And if I slightly redefine my series, the numerator gets even better. The denominator gets as if it's the order curve, as if we're computing if we're computing this expression for n equals 5. And the numerator looks great. This is just the cotangent bundle minus the tangent bundle. These are the characters of the cotangent bundle, the characters of the tangent bundle. And so in fact, it's a natural representation not just of GL3, but SL5 in which GL3 sits. So that's a brief summary of what happened at the end of previous lecture. And now we start new lecture. Any questions about what I said so far? All right. And it's visibly, I already gave you an example. It's visible that this is a character of something on C5. And in fact, so this I said this particular result was conjectured by Nekrasov some 10 years ago, and conjectured not on the basis of let me play with cubes and see what happens. It conjectures on the basis of thinking about something else, namely about a very special 11-dimensional, this is the 10-spatial and one-time physical theory called M theory. And so he took that M theory looks in, like I said, 10 space and one-time dimension. So in particular, for in a time slice, you'll have a representation of SO10 on some it has some certain fields, which we'll discuss briefly in the next transparency. If you restrict this, if you declare your 10-dimensional real space to be a 5-dimensional complex space, then that means you restrict that representation from SO10 to SU5. Then the representation, there's dramatic simplification, and dramatic simplification exactly leads you to this sort of formula. And so the basis of that conjecture was that there's a comparison with fields of M theory. So what's M theory? So this will take, well, for one thing, so there is a difference in which the word theory is used in mathematics and in theoretical physics. In mathematics, theory means a body of knowledge which somehow which already existed. Existing body of knowledge is called theory. In physics, this is something else. This means, how to say? You say you have a theory means you have some way of which you don't, maybe you only know certain features of that. You have some machine to produce, to compute some numbers, but you know only some features of that machine. You might have Lagrangians. You may not know what to do with the Lagrangian. You may not know what to do with that Lagrangian. You may not have a Lagrangian. You may have some. Just theory means some theoretical machine for producing computable, like producing numbers, but it doesn't mean you have that machine. So when you say physicists talk about theory, they mean they suspect there is a way or they know certain features of a certain way, but it doesn't mean it somehow. It's not. Well, I already said that. So anyway, it's expected that there is eventually will be a body of knowledge about a certain very particular theory in 10 plus 1 dimension that includes it includes both fields, that is to say fields. I mean, a field is some kind of tensor space in space-time, but it also contains, in addition to fields, it contains certain extended objects. Like, I mean, nobody, I mean, in the way somehow at this point of age, everybody heard of strings and branes and so forth, and so nobody is particularly should be particularly averse to having extended object in the theory. And so the fields are, first of all, since the supergravity theory, it has gravity, it has a metric. Right? It's since its superpartner is a field of so gravity transforms metric is a symmetric traceless tensor for representation of SO5, and it's and it has a superpartner which transforms in physicists call this representation of spin 3/2. It's called the gravitina, and in addition it has a 3 form, which you should think of as an analog of the vector potential in electromagnetism, and in the extended objects, which we'll talk about. This the point of the next two transparencies about extended objects, but just this field, since just the representation theoretic content gives you a way to compute the index of just the traces of that particular representations of SO5 SO10 on that particular 10-dimensional space. You can compute it. You can see if you're restricted to SU5, you get dramatic simplification, and you get what I had on the previous transparency. So this computation with the cotangent and tangent bundle, out of these 3 ingredients, is going to give you that when restricted to SO5. And now the extended objects, well, so we will talk about the membrane, and the membrane to the 3 form is what a charged particle is to vector potential in electromagnetism. So if you have a charged particle, then its action in somehow electromagnetic action is the integral of the 1 form, the vector potential, along the word line of that particle times its charge. So if you have a particle, it's naturally charged under a 1 form. If you have a membrane, then its world volume would be a 3-fold. And if you naturally integrate the 3 form over that, so it would be the charge of that membrane. So that membrane is charged under that 3 form. And it's that membrane we're going to talk about today. So, all right. Anyway, somehow this conjecture / theorem star is about how you compute just the boxes, how you sum up the boxes in Downs and Thomas theory, where you don't have curves, you only have points, how you sum those in terms of the fields of M theory. Okay, that's now we'll go to a situation when in Downs and Thomas theory we have actual curves. Then we will be looking at the Hilbert scheme of curves in the 3-fold, and this will be summed up using now with the membranes of that M theory. And in fact, so what's remarkable, that seemed to work somehow curve by curve. It's not like so I'll explain what this means. It's not like some big sum equals some other sum. It means we'll explain what it means. So we were talking about previously Hilbert schemes of curves in 3-folds, and we'll be talking about them today again. And these are parameter spaces that parameterize subschemes, or parameterize ideals in the ring of function on your 3-fold. For example, this could be if you in my 3-fold. looks like it has coordinate x1, x2, and x3, I can look at equation which x3 is just 0, but x1 square is equal to 0, not x1. This means my x1 axis is infinitesimally thickened in the direction of x2. Right, so this is the simplest example. To any such thing, I can associate a corresponding cycle. Namely, I take the irreducible components of the support, each with its natural multiplicity. Here, it's clear that this is the x1 axis doubled. So the corresponding cycle is just reduced to reducible algebraic variety with multiplicity. It's just this line counted twice. So what parameterizes this object is called the Hilbert scheme. This remembers a much finer information. It remembers in which direction this line was thickened. Because here I could have, instead of writing x1 square, x2 squared equals 0, I could write x3 squared equals 0. I could write I could have also twisted that. It remembers in which direction it's taken. Here it doesn't. It just remembers what the cycle was, and it assigns its multiplicity 2. So anyway, there is this is called the Hilbert-Chow map. So this means you go from the Hilbert scheme, something an ideal, you go to a bunch of subvarieties with multiplicities. And not only, the point is that this map, not only it forgets in which direction my line was thickened, so it could have been thickened in the horizontal direction, in the vertical direction, but it also could have any sort of further amount of thickening. Like instead of, is that clear that when I draw a picture like this, I mean a particular monomial ideal that's generated by all the coordinates of that three-dimensional partition? So this is the map. This kind of thing means away from the origin. This subscheme just looks just like this subscheme, but at the origin it has a lot of extra thickening, a lot of extra thickness, a lot more functions. Right here, so in other words, instead of here by modding like just square roots of variables, I mod by so for example here. So if this is x3, so I'm modding out by x3 squared times x1 square, right, or something like that. And so in this map, all of that will be forgotten. Because all you do is you look at generic points and the compute multiplicity is there. But so in other words, the fiber of this map is a countable union of algebraic varieties, because if you start with a Hilbert scheme of curves, that remembers both the degree of the curve and its Euler characteristic. It's arithmetic genus, and the arithmetic genus could be here in this case could be arbitrarily large. And the Euler characteristic, is that clear? Every time I add a box, I increase the Euler characteristic of a structure sheaf by 1. So it could be arbitrarily large. But fortunately, the way this generating series is organized is that every time, so generating series will sum up over all possible Euler characteristics with some weight. And so here, if I counted correctly, I had 22 extra boxes. So this will be counted with a weight some variable raised to the power 22. So at least the contribution, like I said, what gets mapped to this cycle is not a finite union of algebraic varieties, but in fact a countable. But from the point of enumeration, it's okay because we have a variable that keeps track of what's going to happen. So in other words of saying is, so I'm just saying again. So it makes sense if you push forward this sheaf to the Chow variety so we have a map which takes the Hilbert scheme and maps it to just the cycle. So that's that, like I said, it's not a proper map, but this sheaf as a quasi-coherent sheaf on the Chow variety is well defined because it has this extra grading by how many boxes I forget. It had that variable, so it's well-defined object there. And to describe that sheaf is another way of saying to sum up the boxes while leaving the curve for fixed curve sum up the boxes. This what does it mean? I had some sheaf on on the Hilbert scheme. I'm going to fix the cycle and sum up the boxes. So that means to say I want to take my sheaf and I'm going to push it forward under that. All right. And so now the conjecture is that this is going to be summed up by those membranes. And so the setup it's not the most general setup, but it's already non-trivial. So let's start abstractly. We want a five-fold with a trivial canonical bundle. That is to say that here, remember in that five-dimensional computation, the product of the t's was 1. So the determinant in 5 dimension was trivial. So with a trivial canonical bundle, we equivariantly trivial. Whatever group action is going to be equivariantly trivial. Now we consider a special, so that z, which was previously some kind of box counting parameter, will now be a variable in the group. So it will be a group, the multiplicative group of the field, C star in this case, acts on that 5-dimensional variety with the following property. It will preserve the 5 form. I mean, all my groups, they all will preserve the 5 form. That is to say, this bundle is equivariantly trivial. And the x will side the x as 3-dimensional variety will sit inside that 5-dimensional as a fixed locus. So just let's go back to this formula. Remember, so we had T1, T2, T3 in 3 dimensions. And we made T4 and T5 so that first of all their product is 1. And then if I take this Z fixed point, I exactly get the T1, T2, T3 directions. So this is I'm going to do something like this, more globally now. So with like a C-star action on a 5-fold, such that fixed point is exactly 3-dimensional. And so for the purpose of this talk, it's enough to consider the following simplest possible instance, when your Z is a total space of 2 line bundles over X. For this thing to be K-trivial, it has to be the case that these 2 line bundles multiply to the canonical. And then the way I want my multiplicative, my Z to act, it will just scale this L1 with weight Z and scale this L2 with that weight Z inverse. Okay? We just sort of globalize the construction of that 2 extra variables. So this is already non-trivial, but it could be there are many examples of this, like you find where this here the fixed locus is connected. You can easy to write examples where fixed locus is disconnected, or we're not gonna. There's something interesting to be said there, but we're not going to talk about them today. And so membranes in Z will be some other moduli space, which is not the Chow variety, not the Hilbert scheme, so you should think of them as one-dimensional subscheme, which in a certain sense immersed. And they satisfy a certain stability condition that does the following. It prohibits, for example, it implies, well, in particular implies they all Cohen-Macaulay. And Cohen-Macaulay implies that there's no way I can add the box. If there's like a box you can remove, you should remove it. So if there's if there's a smaller subscheme such that the difference is zero-dimensional, yeah, you should go to that. You should pass to that. And so this condition, this stability condition that particularly implies Cohen-Macaulay, it makes the fact that if I just fix the degree, then the membrane moduli space is it's a proper algebraic variety. It's bounded. Right? I mean, it's not like the Hilbert scheme. If I fix, so we're talking about the Chow variety at length. If I just fix the degree of the curve, I can add arbitrarily many boxes. For fixed degree, this is not a bounded family. Countable uniform algebraic varieties. But here, if I just fix the degree of the curve, that is an algebraic variety. This has to do with the fact, so we'll talk about this later. And so there's two different maps to the Chow variety you can build. There is a map from the Hilbert scheme to the Chow variety we discussed, that this has big fibers, and we have to form some generating series over that number of boxes so that to make that push forward well defined. And there's some other moduli space, this moduli space of membranes, for which Z has a completely different role. Z waits, now that membrane can explore extra direction. It can move in extra directions. And it moves in extra direction. Those extra directions, they carry a certain weight under Z. Z scales those extra directions. And so when you had your virtual square root of the canonical, you push it forward this way, you have to sum over all boxes with a certain weight. That weight is Z. You just introduce it by hand. Here, there's some some kind of normal directions that gets, how to say, you compute the index. There's some normal directions you have to take into account in this sort of fashion. And those normal directions are going to be weighted by Z. This is how Z enters the formula. So then the statement would be, so there are two maps from two different moduli spaces of slightly different, kind of different nature. Especially different nature is how they both treat Z.
Can we do some sort of micro-localization or something? No, or
no. So there's localization in the sense the following. So if you actually, of course, this what this diagram is contains a certain lie, in that if you have a curve in a fivefold, it doesn't naturally map to the fixed locus. What maps to the fixed locus is the fixed locus in the curves in the fivefold. But that's okay if your fixed locus maps, then if you want to push forward the K-theory class, all you do is you add the normal, then the normal bundle also maps, and that's okay. Well, I'm saying if you think of localization in covariant K-theory, so if you somehow to compute that push forward, all you need to know is what happens near the fixed point, and the fixed locus actually maps.
So it's extra two dimensions.
Yeah.
You shouldn't think of them as being cotangent to the between your three-dimensional and your one-dimensional. You started like that. You have this extra two-dimension you add. You shouldn't think of them as colorful to the curve.
No, I don't think so. No, okay. No. No, I thought that this localization and the fact that this push forward, the definition of the push forward requires certain localization, because the actual moduli space doesn't map, only the fixed locus maps. So conjecture says is that if you push forward, it's just like with the boxes, if you push forward that index to the Chow variety from the Donaldson-Thomas side, this is a symmetric algebra in a certain sense that we'll discuss in a second, or if they push forward from the membrane side. And so, just like before, except this what means symmetric algebra. If you have a sheaf on an abelian semigroup, then you can form like a symmetric algebra over, so you have a abelian semigroup, means you have a product from the n-fold product of your variety to itself. And you push forward the sheaf, you take S invariance. It's like a symmetric algebra over that space. And so in other words, you concretely means if you want to compute a double curve and you want a contribution, if you want to compute the contribution of like a double curve here, what you have to do is you have to count the contribution of like a double membrane, but also if your curve is twice something, then you count the contribution of the actual double membrane, but also one membrane counted twice. And this is what it means. And one striking feature it predicts is that this is well, I mean, it's like a it's not like a module. It's a how to say? It's it's like a you have a anything you compute on this side will be a rational function of z. Just because if you have a like a finitely generated algebra, it's or finitely presented algebra, then it's Poincare series is going to be a rational function. So anything here will be a rational function of z. So it means this thing secretly has some rationality in that which you didn't expect before. And that rationality is already, we observed it. So there was a lot of work done in cohomological Gromwitten-Donaldson-Thomas type correspondences, and there was some rationality observed at that stage. What was somehow not clear is what's the meaning of this rationality? Like, is that should I think of this as a But this conjecture provides a very natural answer. Why is that a rational function? And what's the meaning, so to speak? What's the meaning of that rationality? For example, why it only has roots of unity as poles, no other. So that's and of course you can. Like I said, even the box counting three-dimensional identity, even that you can view as a generalization of like McMahon's enumeration of three-dimensional precision. It's kind of non-trivial identity, and you can of course can embellish this identity. It's going to give a whole. But more importantly, this also predicts a certain dualities, as physicists would say, between different dt counts, and that if automorphisms of my z is large, I can embed. I can take. There could be many one-parameter subgroup that have this different fixed locus inside of the same five-fold. And so then the statement would be that very different dt counts for different varieties are related, in which the box counting variables in one case go to the covariant variables in the other.
So the left-hand side is only x, involves only x.
Involves only x, yeah. So it just says. So this. So I should say I have no idea how to. At the problem is what I'm gonna outline is something which I think will be useful in eventually proving something like this. What it's going to be, what I think it's concretely useful for is to actually compute the Donaldson-Thomas side, and maybe verify that it satisfies the sort of dualities, because the five-dimensional theory, there's some technical issues there which I just don't know how to even start handling. And so, but the general outline is the following. So how it's not the first interesting enumerative prediction made by humans, and the previous predictions were made. Maybe some of you might have heard about this Gromov-Witten-Donaldson-Thomas things, and which is now more or less under more or less total control, and the way you attack something like this is you have something you associate to algebraic varieties. And what you do is you try to first push the formal properties as far as you can somehow try to try to say that, well, if I have some enumerative information I extract from algebraic variety, that if it satisfies such and such properties, that in fact it's uniquely determined on like a finite or maybe like a countable set of varieties, in fact finite. So, so you use some first formal properties to break your varieties in pieces as far as you can tell, reduce the problem to special cases, and the special cases you just compute. So this in principle, it's not maybe not the best strategy, but it's the one that's been most successful. And its advantages is you see two things equal, not, sometimes there are examples of statements in math when you know two things are equal, but you don't know what either thing is. By virtue of my upbringing, the first example that springs to my mind is like Kirillov's classification of representation of nilpotent Lie groups. It tells in terms of orbits. But no, if I give you like upper triangular matrices, like what are the orbits? Like, nobody knows. And so, but it's great to have statements like this which are somehow abstractly true. But it's also nice to have opposite statements, is where you not only two sides are equal, but you also have some kind of way to actually get your hands on either side. And this sort of approach has that virtue. It gives you some kind of algorithm of how to actually compute. And in particular, in particular, this sort of dualities things one can see without, like I said, you can make a progress on Donaldson-Thomas side with just motivation from the M-theory side and not actually, well, anyway. And so right, in particular, you can compute it inside in a certain way, and you should be able to see dualism somehow. This is everything. If everything I'm somehow promising in this lecture actually pans out, then the duality should be there. So I will now discuss what are those formal properties that allow you to bring the very, very general variety down to something unbelievably concrete.
Yes. So is the Gromov-Witten visible from the 5-dimensional picture? Or
no, it's a Gromov-Witten.
Yeah,
actually, Gromov-Witten has big problems in K-theory because this, this Gromov-Witten moduli spaces, they don't seem to be the right objects to study in K-theory. You see, in cohomology, so when you think of some enumerative problem, you can make up all sorts of moduli spaces as an answer, and if you're somehow lucky, it's sometimes very difficult to guess wrong, because in cohomology, there's some dimension, right? So if your moduli spaces up until certain dimension look the same, then it's okay. Yeah, but in K-theory is very non-forgiving. If you somehow didn't get the right definition, then it's just the answer comes out wrong. And it seems like in this story, just the whole Gromov-Witten theory is one should somehow rethink it. It seems like it'd be great to have some people continue to be super interested in like the Euler characteristic of like long bundles on the moduli space, of course, would be the simplest possible Gromov-Witten type K-theoretic computation. That's pretty hard. So I'm going to talk about these formal properties. So this is part 4, and we'll start with an obvious remark that so ideally you would like to deal with manifold by cutting them into pieces. Somehow directly doing this with Donaldson-Thomas like spaces is bad, because if you cut up, the point is that if you cut up, you had a complete curve. It's deformation theory somehow under control. If you cut up it in pieces, then it's not so good. But there is a very good way to break to break up algebraic varieties in pieces. Namely, if you have a degeneration in which, so the best possible degeneration of algebraic variety into two pieces, you have a family, total space of the family is smooth, and it breaks in the special point, your variety breaks in the union of two along a smooth divisor. It's like xy equal epsilon type of degeneration. And many people worked on how to extract a numerative geometry. So that means you've broken up a more complicated variety into a union of simpler one along a divisor. Many people worked on extracting a numerative information of x from these two pieces, x1 and x2. But I think the crowning achievement is the work of Pandey and Pixton. So their work was on this Grom-Witten, this MNOP type conjectures, and they've shown that they have a way to trace this Grom-Witten, Townsend, Thomas through this sort of degeneration, and much of and some certain key steps on that they can be lifted to K theory. That's good news. And previously, Pandey and Levin showed that in some sense you can, in certain precise technical sense, if you have that move, you can break up any algebraic variety into a toric variety. In fact, product of projective spaces. So if you have this move, then that's enough to do it for toric varieties. So now with toric varieties, there's a further way to break them. Namely, we've talked about localization many times. And so if we look at the Hilbert scheme of curves in the toric variety, so here's a toric polygon that corresponds to P3. This is the moment polytope for P3. This means toric variety, well, it looks like a polygon in that it has a strata, which are tori of different dimensions, corresponding to their complex dimension is the same as the real dimension of that strata in the polytope. And here, so like P3 has 4 fixed points corresponding to 4 vertices. It has 6 torus fixed lines corresponding to joining those vertices. So these are the picture here. Are the corners of that polytope are the 4 torus fixed points on P3, and the edges are the lines that join them. So if we look at the point, the fixed point in the Hilbert scheme of curves, first of all, the corresponding cycle is just a bunch of those lines because it has to be torus fixed. And then further, the thickening, how the thickening is going to look like. So at each vertex, it's going to look like one of those pictures that we've seen, except it now has 3 legs somehow extending to infinity, and these legs will have to be glued along the edges to form a scheme. That clear? So anyway, so if you have a toric variety, then curves in it, in certain very precise sense, are all enumerative information in some extremely precise sense is obtained if you know just this one, just like a C3 thing. And how when there's some kind of gluing matrix. It's another very simple thing. That's the key point here. To know this sort of thing. This sort of thing means you should think of this here. So here's it's a monomial ideal in 3 variables that kind of ends up on 3 monomial ideals in 2 variables. So it's a 3-dimensional partition that ends on like 3 2-dimensional partitions. So this is like a tensor which label are 3 partitions, or maybe better to say it's a tensor of which labels are 3 K-theory classes in the Hilbert scheme of points in C2. And so if you have this piece, then you can do any toric variety. Right? So in some sense. You see, here we use the fact that once you go to the toric variety, then the covariance is enhanced. And if your conjecture is a covariant, then you should be able to do this. So it's not so Now, there's a little technical trick that here, instead of this trivalent tensor, it's much easier to think about a different trivalent tensor. Namely, look at AN surfaces. AN surfaces are minimal resolutions of quotients of C2 by a cyclic group acting, like roots of unity in one variable and the inverse of them in the other variable. So usually people draw the A1 singularity, which is a cone, and here I've drawn this A2 singularity, which is something like this. It looks different on my screen than it looks here, but anyway, it looks something. So its minimal resolution would be a surface which has the exceptional divisor are two P1s, which intersect transversely. And so now if your geometry is that surface cross C1, then a curve, like a one-dimensional curve, which is, how to say, which is, particularly you can study curves that look like this, that look like they have some kind of thickness along the. So my toric polyhedron for this geometry, it's look like a product of. It looks like this. The toric. The toric picture for A2, which is that sort of. It looks like this, and then there's three legs, and now I can study my curves that have some life inside my A2 surface and also come out to be three partitions. So it's again some kind of tensor, has three partition labels, but what these labels are, instead of being elements in the product of the Hilbert scheme of three Hilbert scheme of C2, you have an element in the Hilbert scheme of A2 surface. That's what it somehow means. But it's a space of the same size. And so it's elementary to see that if you know this tensor, then you can solve for this middle bit. And so if you know this, then you know everything. In some sense. And so the statement is, so this tensors, so like I said, this is a tensor which is a label, is a label. It takes an element in the covariant K theory of the Hilbert scheme of AN surface. That vector space is a module in which I'm going to explain in the next lecture, is a module over some quantum group, namely this kind of funny thing. So this differs from something. Well, anyway, somehow there's some very interesting quantum group, and so we got here to the end of the title, and. So, in case, I don't know. I ran out of transparencies 2 minutes too early, but my plan was to show them all in the first lecture. So you can ask what's Q in this, and Q is in fact the weight of the. What's the? Is this? To say the weight. So A2 surface is symplectic, and the holomorphic symplectic. It's the weight of that holomorphic symplectic form. Yeah, they're hats. They're two hats. So. It's like loops in the loops, yeah. Oh. Loops and loops, yeah.
Okay, double loop space?
Yeah, right. So it's some deformation. What this thing is, it's a certain Hopf algebra deformation of GLN tensor Laurent polynomials in two variables. You take any Lie algebra. You can tensor it as polynomials. You get some kind of Lie algebra. Take universal enveloping, and you can ask for Hopf algebra deformations of that. In general, this is big kind of I don't know, but in this particular case, it's something super nice. So, and it's all right. So I don't know. Maybe I'll maybe I won't say anything more since I don't know. We'll just sort of end 2 minutes early. Now even 1 minute early. So